matric choice 2, 26th of June, first half an hour starts.
Action.
No, action.
Sure, you're never going to get a job in the farm industry. I don't know, all this training, maybe you will get a job in the farm. Right, we're ready, we're going. We need to go really quickly because some kids have to leave really. Put that mask on, Kerry. Nasal rings increase the likelihood of getting COVID. Studies have been done. No, I'm lying. Sorry. Yeah. Step away from that child. The face? And the face? There's no face. Promise me. Because if you've got a face, you have to tell me. You can't just get a face and not let me know. Okay, right, moving on. Okay. So guys, basically we've got 4 weeks left to finish the whole syllabus. So we've got the whole of evolution and the whole of genetic engineering. Kerry, put that. And who are all these brats that are missing? Pardon? Yeah, Kellen's not here, but who normally sits here? Who normally sits there? No, man. Who's Michelle?
She's not here.
Who's Michelle?
Oh.
Say again?
Michelle King.
You have to give me a surname. If you don't give me a surname, I don't have a picture. Sorry. You know how many kids I teach? You know how many kids I've taught in my life? You say Michelle and I'm going, who's Michelle? Give me a surname, then I get it. No, okay, then I got it. Okay, right, going. Tabsy, are you singing in my class?
No, my name is Amu, I swear, man, I couldn't sing. Can you imagine? I could never believe.
Okay. Right, going. So we've got, today I'm going to just quickly run through polygenic inheritance. And then next week, we're going to do genetic engineering. Our recommendation is everybody be at school. Okay. And let's go. Okay, so I've touched on this before. Okay, when I dealt with skin color, I mentioned it before. Can anybody see? Oh, got it. Okay, so obviously, you know about a gene. Okay. So far, we've dealt with situations where it's a characteristic is controlled by a gene at one locus. Okay, so we've spoken about in pea plants, there's red flowering pea plants, or the allele is white flowering pea plants. So in pea plants, there's one gene, or a gene at one locus that controls color of flower, or height of plants, or color of seed, or whatever. So there's only a single gene, a single gene at one locus that controls that particular characteristic. But there are other characteristics which are controlled by genes at different loci. So a gene here with perhaps two different alleles or the same alleles, and on a totally different chromosome, a different gene which is also involved in this process, and even possibly, as in the case of skin color, there's another gene somewhere else that is also concerned with controlling skin color. And so it would be the outcome of it, the phenotype, is what is the genotype here, what is the genotype here, and what is the genotype here. And so the number of different combinations, and I do think it might be 64, but I might be wrong. Anyway, it doesn't really matter. It's just that you can have all those different genes are involved in the phenotype. Okay, and so it becomes quite a complicated thing. And if you look at the range of different options and plot it on a graph, you'd get a bell-shaped curve. So let me just show you in terms of the curve. If you measure all the different options and plot it on a graph, you'd get, Matthew, a bell-shaped curve. Okay, you all know what good old friend bell-shaped curve is about, hey? Yeah. Okay, so height, for example, human height. You measured everybody's height. It's not you get only short and tall. You get a whole range in between. And that's because height is controlled by more than one gene. There's a gene at one locus, a gene on a different chromosome, etc. Okay, so some of the features of different organisms in a species show what is known as continuous variation. Other features show discontinuous variation. Okay? So if you look at this, this is continuous variation. Human height, continuous variation. It's not in very specific, you don't get anything in between categories. You don't get short and tall. Okay, all right. So human height is an example of a characteristic with continuous variation. Height ranges from the shortest person in the world to that of the tallest person in the world. And any height in between these values is possible. And so it's called continuous variation. So for any species, a characteristic that is continuous, in other words, changes gradually over a range of values, shows continuous variation. And examples are height, weight, and skin color. There are other examples. Pardon? What, Tabzi?
Miss Ma'am, I swear it's Amu.
Nah, I thought that one was Amu. Yeah.
What?
Okay, moving on. Okay, so when the height of a group of people is measured and a graph of the results is drawn, it usually looks something like this. So you can see there the height categories, and you can see the little columns, and if you do a line to show the trend, then obviously it is a bell-shaped curve. If you had to draw this graph, what is the one thing that you would do differently to make it correct? Because it's not a good graph. You'd lose marks. Okay, if you consider height categories, what type of graph should you do? So not a line graph, we have not a line graph. It's got to be a column graph. Are you going to do a histogram or are you going to do a bar graph? A histogram. Because the height categories are continuous. So if you read these figures, it's less than 130, then 130 to 134, 135 to 139. There's no gap in between them, and so these columns should actually touch each other. And so it's a histogram. Should be drawn as a histogram, not a bar graph, and they've drawn it as a bar graph. How do you know the difference between a histogram and a bar graph? Which one's got spaces? How do you know that? Well, I don't know. It depends what your objective is when going to set a bar. Okay, I've got a totally different way of remembering it, but apparently Williams is quite a good one. If you look through the window and you look through the bars, there's spaces between the bars. Regular bars, spaces between the bars. And so a bar graph has spaces between the columns. Histogram doesn't. So continuous variation is always the combined effect of many different genes. And therefore, many, maybe two, eh? And therefore it is known as polygenic inheritance. It is possible to also have environmental effects. So if you consider skin color, for example, so while it is genetically determined what skin color an individual would have, spending more or less time in the sun would affect the outcome, the phenotype in the end. Okay? So certain characteristics that are controlled by polygenic inheritance, just like with ones that are not polygenically inherited, have environmental effects as well. Okay. An example would be milk yield in cows is determined not only by their genetic makeup, but also significantly affected by environmental factors such as the quality of what they eat and their pasture, the type of food that they eat, the weather, the comfort of their surroundings, etc. So cows will give different milk yields depending on those environmental factors. The important thing you have to know is it's non-Mendelian. So remember, Mendel had the whole thing about you get a dominant gene and a recessive, and if two heterozygous organisms are crossed, you're going to get a 3:1 phenotypic ratio and a 1:2:1 genotypic ratio. That's all Mendel. It's dominant or it's recessive. There's no midway in between. Okay, and there's one gene. Mendel also, he didn't call it a gene because genes hadn't been discovered at that stage, but one factor that controls each characteristic. Okay, so polygenic inheritance has been worked on since Mendel's day, and so it's non-Mendelian in principle, and it's when a trait is controlled by more than one gene. Example, in human skin color, height, and weight. So here you can see a whole range. These are the leaders in Europe at one stage of the game. Okay, here's Obama. Not Europe. I do know it's not Europe. Sorry, the world. Is Angela Merkel. Okay. And here's a skin color range. So remember that there are three different loci involved, genes at three different loci that are involved in skin color. And so each gamete would have three different genes. So in this case, it is big A, big B, big C. And this gamete has big A, big B, big C. And so the individual is homozygous A, homozygous B, homozygous C. And that would give the darkest possible skin color down to little a, little b, little c, and this is the lightest skin color. Not to be confused with an albino. Not an albino. An albino is lack of skin pigmentation at all. So the eyes are red quite often. No color in the eyelashes, the hair, etc. Who are you busy marking? Here's... I'm not going there. Okay, right. I'm listening.
Is that like the ratio at the bottom?
No. It's showing the range.
Oh,
maybe it's a... you know what it is? It's a bell curve.
Oh.
This is the proportion. This is the proportion. So, you know, when I go 3:1, normally, there's 3 of these to 1 of that. This is 1 of those to 6 of those to 15 to 20.
So like, if I look at like the world, that
Yes.
would be the kind of...
Yes.
And then what happens like when, like,
Dash.
a mixed
Don't
race,
drop.
a mixed race couple like has twins and then one is black and then one is white.
So remember that the whole thing is that if you're talking about a mixed race couple, that this individual could be heterozygous for all of them, and this individual could be heterozygous for some of them, and so the gametes that they produce are not the same gametes. And remember that non-identical twins are the same as having siblings. It's different sperm, different ovum. Right, so the greater the number of people measured, in other words, the bigger sample size. And you say sample space. I don't know where you get the stupid sample space from, but you're going to get a stupid 0 mark. Joshua!
Yes, ma'am.
Okay, you're going to get 0. Okay, sample size. And the smaller the categories used, the closer the result will be to the curved line, to that bell-shaped curve. The shape of the graph is typical of a feature with continuous variation, and weight would give a graph similar in shape to that one. Discontinuous variation. This normally comes from having a gene at one allele that controls this, and there are only a limited number of possible values. Human blood groups is an example of discontinuous variation. So there's only one locus for human blood groups. There are a number of different allele types at that locus though. So there's A and there's B and there's O. Yep.
What about RH and L?
It's a different thing. That's like you can talk about skin color and eye color. It's two different things. It both happens to be on the body. Now it's exactly the same with blood groups. So they're two unrelated things, rhesus factor and blood group. They both happen to concern red blood cells. And so they're always put together, use A positive or whatever, but they're unrelated to each other. We do know that, do you guys know your blood groups?
No. I mean, personally, like with our own, like, oh yes, no.
Okay, who's A? No, I'm not going to ask that. No, I'm not going to ask that. Okay, moving on. In the ABO blood group system, only 4 blood groups are possible, A, B, AB, and O. So this would be a person who is heterozygous AB. Okay. There are no values in between it, so it's discontinuous variation. And an example of this is the blood groups, and this is inherited in the Mendelian way. Pop it up, I'm nearly finished, okay. Right, so it would be represented like that, okay. So this is definitely a bar graph, it's not a histogram. Good luck. No, you can't all go. Only the people who are writing maths live.
End of first half hour, matric choice 2, 26th of June. Cut.
Okay.